we want to continue with planar graphs, and we want to give a characterization theorem when are planar graphs planar. Okay, so what do we already know? We already know that K5 and K33 are not planar, right? K5 we proved in class using like almost not even really topology, but just some basic reasoning in the plane. That K33 is not planar is one of your homework assignments to do it in a similar fashion there. Actually, you'll end up proving it's not planar in more than one way. But those are the only two concrete ones we've seen. Let me draw another one to give us some idea about what is and isn't planar. Okay, so we've got two vertices here. I don't know, I guess they're named S and T in the picture. They don't really need a name. And then there's a path here. So you have this long path here from V to U, say, and this path can be of any length. So the purpose of this illustration here is to show you graphs that are not planar for any number of vertices. So this graph that I'm going to finish drawing won't be planar, and I can add vertices to this path to make a graph with more vertices that's not planar. So for any number of vertices, at least 6, okay? So it continues to look like this here. So S and T are adjacent to everything on this like middle spine here. I'm going to erase this last one here. I don't want to draw all these. All right. So far, not so good, right? What I've drawn is planar. So like, I mean, like we need some more edges. And actually, I'm just going to draw one more edge, this one here from U to V. Okay. And I claim that this graph is not planar. The proof is not there's a crossing edge, right? You're planar if there's an embedding with no crossings. I drew an embedding with crossings that doesn't preclude the the possibility of a better, smarter drawing. Okay, so just keep that in mind. That's an easy mistake to make at first. Just because I've drawn it with a crossing doesn't mean it's non-planar. In fact, in the first class on planar graphs, I drew a K4, right? Just maybe to re-emphasize this point. That's K4 drawn with a crossing, but we can draw K4 without a crossing, right? And this is proof that it's planar. Proving something's not planar is harder, right? It's harder to do. However, we have a couple tools at our disposal. I don't know why I did that. First of all, if the graph contains K5 or K33 as a subgraph, then there's no way it's planar. Because if I could draw it planar and K5 was in it, then I drew the K5 planar in there as well, right? I somehow drew every subgraph with no crossing as well. So if these things are subgraphs, you're not planar. Okay, great, that's one thing. You can also try to argue that it's not planar through just pure reasoning that, oh, if this vertex, these vertices are inside of a face and it's a triangle and blah, 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 you might be able to do that. There's another tool that we learned last time as well, though, about planar graphs, the edge bound, right? So recall edge bound, it's the planar edge bound. That a connected planar graph, actually it still holds for non-connected. The number of edges in a planar graph is at most 3 times the number of vertices minus 6. So if I give you a graph that has more than 3n minus 6 edges in it, there's no way that it can be planar because it violates this bound here. So that's another tool in your toolbox for showing something's not planar. In fact, maybe we didn't do it, but this actually implies that K5 is not planar, right? Because K5 has 10 edges, but 3 times 5 minus 6 is 9, right? So the K5 actually violates this thing here, okay? But this is not an if and only if. There are graphs that have more edges than this. Sorry, no, that's not what I'm saying. What am I trying to say here? You can still be non-planar and have fewer edges than this, right? That's what I mean to say, right? If you're planar, you're definitely below this, but you might be way below it. Okay, so it's not some kind of if and only if. So, wait, what? Yeah, right. Okay, so this one's good here, but like, okay, actually, maybe since I said that, let's clarify here. K33 doesn't actually violate this here, right? It has, it's the planar edge bound says that this can have at most 6 vertices times 3 minus 6. It can be at most 12 edges, but K33 has 9. So it doesn't violate the planar edge bound, but it is not planar. Okay, so violate, did I say that right? It does not violate this, but it is not planar, right? Okay. But this graph up here, we can check real quick, does violate the edge bound and therefore cannot be planar. Okay, so like this drawing here is reasonable. Somehow I have to have a crossing. Okay, let's just double check real quick. So let's call this G, number of edges. And let's say it has n vertices. Okay, so it has n minus 2 on this middle path here, and then S and T are 2 more vertices there. Okay, so the number of edges is, well, let's count it this way. S and T each have degree n minus 1. N minus 1, right? S and T are actually adjacent to every other vertex in the graph. And let's not count by degrees exactly. Let's just count edges carefully. So S sends edges to the path there, and so does T. So S sends n minus 2 to the path. T sends n minus 2 to the path, and then there's one edge between S and T. Okay, I'm avoiding double counting edges, so I don't have to divide by 2 or anything like that. And then the path from V to U is actually a cycle, right? It goes V, goes to the next one, all the way to U, and then goes back along the red edge there, which I drew specifically. Okay, and that contributes another n minus 2 edges, right? It's n minus 2 vertices with the cycle covering them all. There's n minus 2 edges. And this comes out to 3n minus 5. Right? 2, 2, 2 plus 1, which is too many. Okay. There's 3n minus 5 edges, which means there's no way that it can be planar. Right? There's one more than we're allowed. Okay. What it does say is that if I remove one edge, I can't say this anymore. Right? I can't violate this anymore, and it may or may not be planar. In this case, you can look, if I remove the red edge, it's clearly planar. If I remove a different edge, maybe, maybe not. Right? Again, just because you drop under this thing doesn't mean that you're planar. I actually have no idea. If you drop, in fact, no, I know if you drop other edges, like if I were to drop this edge here, I think I don't become planar. Okay, I think I don't become planar. The reason being is like, if you just look at this drawing here, like the red edge is still somehow gonna have to cross these guys. That's a highly non-rigorous statement though. Again, there could be a totally different drawing, but like somehow this edge doesn't save you from the problems the red edge causes you. Actually, maybe an easier way to see it is if I remove a vertex here, I'm clearly going to have the same problems, right? I mean, I'm going to drop by, well, okay, it's not quite clear because I'd have to connect these up, but anyway, okay. But that's basically what I want to cover in the next step here, is that this graph is not planar, right? We just proved that. And I want to convince you that it doesn't have K5 or K33 as a subgraph. So it's kind of a new type of non-planar graph. Because again, if it contained K5 or K33 as a subgraph, then this was just like, oh, I just added stuff to graphs that were already not planar. It wasn't interesting. It wasn't new. Okay. So that it doesn't have K33 as a subgraph, that'll also be a homework exercise. So I won't do that. But okay, so this says, so G is not planar. Okay, this is fact number one. Fact number two is no K33 subgraph. This is a homework. And then, I mean, it's not very hard. And then I'll prove to you real quick that there's no K5 subgraph either. And let's look at that real quick. Okay, so if this graph contains K5 as a subgraph, there's something you can tell me about the edges of this drawing here that are in my K5. Anybody able to reason something out? Like if K5 is a subgraph, I use 5 vertices in the picture, certainly, and I use 10 edges in the picture. But can you say anything concrete? So a K5 must use the red edge. Why? Why must a K5 use the red edge if it were a subgraph? Anybody see that? It's something to do with planarity. Forget like, other reasoning. If I remove the red edge, the graph is planar. Just look at the drawing there, right? So if K5 is a subgraph of the black edges only, then K5 is a subgraph of a planar graph, right? This graph minus the red edge is planar. K5 can't be a subgraph of a planar graph because K5 is not planar. We've already proved that. So if it's here, it's using the red edge, right? It's got to use the red edge, okay? So otherwise, K5 a subgraph of a planar graph, right? Which is contradiction, okay? Nice little bit of reasoning to get us part of it. Okay, great, whatever. That's one of the 10 edges, but actually more importantly, it means that vertex V and vertex U are part of a K5, okay? Any pair of vertices in a K5 are joined by an edge, okay? So that means I need 3 more vertices in this graph here that are adjacent to V and U simultaneously, right? That's the only way to get a K5, okay? So we need, I'm gonna just write, need 3 more verts that are both adjacent to U and V. And now just by inspection, how many vertices are adjacent to U and V simultaneously? Yeah, 2. S is, T is. And if this path is too short, actually there could be one more, right? If there's one more vertex along this path here, like if it was only 1, 2, 3 vertices, then they'd both be adjacent to it. So I should actually say here that this one should be on n at least 6. Okay. Otherwise, if n equals 5, this graph is a K5. Okay. So yeah. And then it of course contains it as a subgraph. So this is somehow related to a K5, but as I stretch out this middle cycle here, this middle path here, U and V become farther and farther apart, at least in terms of a middle vertex. Okay. So but only 2 exist. Oops. Okay. Which is a contradiction. Okay, so it doesn't contain a K5. That it doesn't contain a K33 is a similar argument, although for that one you're going to need to have at least 7 vertices. I think maybe, I'm not 100% sure, but I think when n equals 6, I think you actually might get a K33. Maybe not. Maybe you get K33 plus an edge or something like that, or plus a couple edges. But I don't want to go through the details. That's for you guys to prove. Okay. Okay, so great. It doesn't have a K5 subgraph. It doesn't have a K33 subgraph, and it's not planar. So it's kind of some new type, or at least it doesn't follow those two. But that doesn't say anything on its own yet. So let's build up another piece of notation here that's going to get us all the way to describing when a graph is and isn't planar. Okay. So definition. So a subdivision of an edge xy replaces xy, the edge xy, with a path xzy, where z is a new vertex of degree 2. And let me maybe add this, and x, y is not an edge anymore. Okay, so if we're working with a graph, I don't know, say, let's just use the K4. It's my favorite standard example here. So here's a graph here, and say this is edge xy, and I'm saying, hey, I'm going to subdivide the edge xy. That means I just add a vertex z in the middle like that. That's all it is. It's very simple to draw into the picture. I just add a vertex z. Now look, x and y are no longer adjacent to each other. Z is a degree 2 vertex that's on this path x, z, y. Okay, so this is a simple example there. That's a subdivision of that edge. And actually, what we're more interested in is the definition of a subdivision of a graph. A subdivision of a graph is just like repeated applications of subdivision however you want, right? If you do subdivisions multiple times along edges and different edges and so on, the resulting graph is a subdivision. So if I give you a graph, there's infinitely many subdivisions. Each of them is called a subdivision. Okay, so let's say a subdivision of a graph G is result of, how did I put this? Any number of subdivisions of edges. Okay, I won't say of G just because when you subdivide, you get a new graph, and then you subdivide that graph, then you get a new graph. It's just a series of graphs. So like, let's look at an example, although you can actually perform these simultaneously. let's look at K4 again. So you start with K4, and you can just do a bunch of subdivisions. Say you subdivide this edge multiple times, right? And that makes sense because, like, look, when I subdivided here, I could subdivide again there, and then again there, and then again there. Like, you can keep subdividing along subdivisions. And so actually, in fact, you'll see in some books, when defining the subdivision of a graph, they'll say what you do is you replace an edge with a path of whatever length you want with vertices of degree 2 along it. But you can replicate that by just multiply subdividing it. Okay, so say that edge is subdivided a bunch of times. Say the bottom edge was subdivided once, this edge was subdivided twice, I don't know, once, and maybe these two were untouched. Okay, so this is a subdivision of K4. But there are others, right? I mean, like K4 itself is considered a subdivision of K4, right? I perform 0 subdivisions. Or maybe I do this nice one where I subdivide every edge exactly once. That is also a subdivision. Okay, obviously there's infinitely many. I can keep lengthening these paths. Okay. Now, subdivision is kind of like, it's sort of like the inverse of a contraction, sort of, but they're not actually inverses of each other. Clearly, by contracting, I can get rid of these subdivided edges, right? Like if I want to undo this, I can just keep pulling these vertices to y, right? And then they'll all vanish, and they're all degree 2, so they don't accumulate any like loops or multi-edges or anything like that. It just eliminates everything. It makes y adjacent to x again. You could go in the reverse. There's multiple ways to contract it, but when I contract, you know, a pair of vertices, like pull these guys together and, you know, make a new one, subdividing doesn't undo that, right? Subdividing only introduces vertices of degree 2. And so subdivision doesn't undo contraction, but contraction does undo subdivision. Okay, so they're not inverses of each other, but there is a relationship between the two of them. Okay, so let me actually write this, although it's not terribly rigorous, but that subdivision or contraction can undo subdividing, but not reverse. Okay. We talked a little bit about this when we were thinking about contractions, and actually trying to find an inverse of a contraction is not like, it's basically not really possible. There's just multiple like sort of different outcomes here, but subdivision is very, very nicely defined, right? It's very simple what's going on here. Okay. And so if I'm talking about a subdivision of a graph, I can arrive at that graph through contractions. I can get back to my K4 by contracting in the appropriate order. Okay, that'll be handy fact for us. But let's think about subdivisions for a second. What's a subdivision's effect on a graph's planarity? So how does subdividing, I like to think of subdividing as an action that you do to the graph, right? The result is a subdivision, but this can be thought as subdividing the K4, right? It's the result of multiple subdivisions. Impact planarity.
So it shouldn't impact it?
Come again?
Oh, I think it shouldn't impact it.
Yeah, exactly. I got a few answers here. Yeah, exactly. So it shouldn't. You guys are right. So it doesn't. Okay, and I'm not going to prove it beyond this observation here. The formal definition involves looking at Jordan curves and stuff, but actually, like if you look at a planar graph and think about it for a moment, right? If you just ignore all the subdivided edges, like along this guy here, and say, okay, I started with K4 and it was planar, and then I did a bunch of subdivisions. I mean, so this is clear that I maintain planarity because like edge, I didn't even change the geometry of the graph. I just put these infinitesimal dots along the line. Like if there were no crossings, they don't magically appear. Now the reverse direction is less clear. It requires a little more thought. Suppose my graph is not planar and I do a bunch of subdivisions. Can it become planar? And the idea is basically the same, that you can't magically make it planar because same reason. Ignore all the subdivisions and just look at that path as a single edge. If I could somehow embed it with the dots along it with no crossing, then I could embed it by ignoring the newly introduced vertices as well without crossings, right? The existence of a vertex here along this doesn't help me. It could help me if it allowed me to like travel through here via edges, but there's no such edges, right? I didn't introduce edges inside the middle there. So like just ignoring what's been subdividing just says, hey, like you can't, if you couldn't do it before, you can't do it after subdividing, and vice versa, okay? So yeah, and to be a little more formal, yeah, you could talk about like that these paths are just Jordan curves, even if they were just edges. Or not, they're not Jordan curves, right? Because they may not be closed, but it's just a curve in the plane, right? Okay, so it does not, let's put like via a little topology. Maybe you don't even really need topology to get that. Okay, so planarity is unaffected through subdivision. It's actually unaffected through contraction as well. Okay, that's not true. If you're planar and you contract, you stay planar. If you're not planar and contract, you might become planar. I mean, if you think about contractions, you can contract until you get to a graph of a single vertex with like a bunch of loops, which is planar, right? So like that contraction goes in one direction. You'll stay planar, but you might become planar as well. Okay. Anyway, that's just a side note. Okay, so it turns out that this subdivision property here is in some sense strongly related to whether or not you're planar. Okay, let me write out the theorem here. Okay, it's called Kuratowski's theorem. Maybe from like 1937 or something like this. This is not one of the, the big 6 equivalent theorems, but this is one of the big 10 theorems of graph theory, definitely. So a graph G is planar if and only if, we love statements if and only if, statements like this, it contains no subdivision of K5 or K33. So K5 and K33 are super important here, right? Somehow they still are the only impediments to planarity, except it's just not just these as subdivisions, but it can't contain any any subgraph. So let me emphasize as a subgraph. Remember, when we say contains a graph, it means as a subgraph. So you're planar if and only if you have no subgraph isomorphic to a K5 or K33 subdivision. So you may not have K5, you may not have K33, but you don't have any other subdivisions, okay? Like none of the, I mean, yeah, so it's not enough to say that you're K5 free and K33 free. You have to show that you contain no subdivision. Now, if you think about that for a minute, that's nice. I mean, it's a if and only if, it's a characterization, but how do you show you have no subdivision isomorphic to a K5? There's actually infinitely many of these, right? If I give you a K5, there's tons of different ways to subdivide them, right? So actually, it turns out this can be used to check planarity quite easily, like in practice. But there are many subdivisions of a K5. There are many subdivisions of a K33, and in principle, you have to check both, all those examples, whether the subgraphs or not, which could be complex. But as we discussed, and one of the reasons it's easy is, the drawing of a subdivision of a K5 and a K33 like basically look the same. Like subdividing them doesn't matter. Okay. So we're going to prove this or some closely related theorem in a minute here. I just want to go up here and look real quick. So what it means is this non-planar graph should contain a subdivision of a K5 or a subdivision of a K33, right? It ought to be there by Kuratowski's theorem. And it's not super easy to find necessarily, but maybe I won't. Yeah, okay. So we can actually find it. We can find it. So if I take these 5 vertices, S, T, V, U, and 1 vertex on the center here, then, okay, there are additional edges in addition to the K5, but where's the subdivision? I've got 1 vertex, 2, 3, 4 that are all adjacent to each other pairwise. And then I've got a 5th vertex here that's adjacent to S, it's adjacent to T, and then it's adjacent to V along a path with 2 vertices of, okay, their degree is higher than 2, but I can throw away these intermediate edges. And also a path here between, let's call this X and U, right? So that my picture looks like this is S, T. So S and T are adjacent, U, V are adjacent. So all these vertices were completely adjacent to each other. And then X was adjacent to S also and adjacent to T. and then it wasn't adjacent to U or V, but it was joined by a path. That this had additional edges coming out of it doesn't matter, right? Because I can ignore those. And actually, yeah, I mean, I'm just throwing away these additional edges. They're just further away. Like these paths also send edges to S and T, but whatever. That only helps me. I'm saying I have a subgraph that's a subdivision. Okay. So I found my subdivision. You might also be able to find the subdivision of a K33. Right? It doesn't say it one or the only other. It's definitely got at least one. Okay. There's another version of Kuratowski's theorem. Well, version, I mean, it's a different theorem. And sometimes that one's a little bit easier to work with. And let me state that one, although we're going to only prove Kuratowski's. This is called Wagner's theorem. I don't know if this is stated in the notes. It really should be. But it says that, let me just say it in words here. So it says that a graph is planar if and only if you can't somehow contract and get a K5 or a K33. Okay, so you can't contract some subgraph and get a K5 or K33. Sometimes we call this thing a minor, or that like a minor of the graph is like you can result in contractions and get it there. And that's also an if and only if. And actually, if you think about it for a little while, this Kuratowski seems stronger than Wagner's because of this like reversibility thing. But Wagner's is a little bit easier to think about sometimes because like if I asked you the question, we go back up here and say, can I do contractions and get a K5 subgraph? That seems like a more workable goal. Like I don't have to try and like find the subdivision. I can just say, let's do contraction tricks. And what I do, I take this middle path and contract it all to X. And then V would be adjacent to X, U would be adjacent to X, S and T would be adjacent to X. Everything would be adjacent. But I mean, that's of course the same as this picture here. And then I just contract along these edges here, okay? But it's just a different characterization, okay? I'm sure it's stated in both textbooks. So let's say look up. But I did state it for you, okay? I just don't want to go through the terminology for what like the result of a contraction is and so on. Okay, so we're not going to prove the Kuratowski's in its full generality. I'm going to prove Kuratowski's under the assumption that G is 3 connected, okay? The reason I'm going to do that is the 2 connected and 1 connected cases are annoying and just technical, and they follow up from the lemma that will be for the 3 connected case, but it's not worth our time to go through it. And I'll even hint at kind of why. Like if your graph has parts that are like 1 and 2 connected, it's pretty easy to show that they are planar if they don't have K5 or K33. Okay, it's just kind of a mess of things though. Okay, so okay, first of all, let's suppose we're actually proving the full Kuratowski's theorem. The forward direction at least is immediate here because subdivisions of K5 or K33 are not planar, right? We already discussed this. So G is not. Right, that's the contrapositive of this direction here. We know the subdivisions of these are not planar. If you have subgraphs that are subdivisions of these graphs, then your graph can't be planar because these can't be drawn. Those graphs can't be drawn planar. Okay, that's the easy part of the theorem. Those are obvious impediments to being planar, but the reverse direction is the more interesting one. And like I said, we'll only prove the following lemma that says if G is 3 connected and has no subgraph K5 or K33 subdivision, then G is planar. Okay, so this is the obvious thing that we want to, like the interesting thing to prove here. This 3 connected here is an additional case. Like without this, we should be able to prove it as well, but use this lemma and a bit more work and you can get it. And we have none of these forbidden subgraphs, right? We have no K33 subdivision, no K5 subdivision. How do we convince ourselves that G is planar? Well, we're going to find a planar embedding somehow, okay? And these things are going to be roadblocks. And we're going to show that there's circumstances where I can't draw it without crossing edges, but those only occur if I had a K33 or K5 subdivision, which would be a contradiction. Okay, so the proof is by induction. So we're proving the lemma. Okay. Once we prove the lemma, finishing Kuratowski's theorem would only requires us to consider graphs G that are not 3 connected. Okay, so they have sets of fewer vertices that can disconnect them. We'd have to go through those. We won't, but that's what we have to do. Okay, so induction on n. N is the number of vertices of G. Okay. The smallest case for which the lemma makes any sense is for n equals 4, right? You don't have 3 connected graphs on fewer than 4 vertices. And actually on 4 vertices, there's only one 3 connected graph, right? The K4, the complete graph on 4 vertices, which just so happens to have no subdivision of K5 or K33, merely by the fact that it doesn't even have 5 vertices, right? So like K4 is the only graph that satisfies our theorem here. It's the only one that's 3 connected on 4 vertices, and it trivially satisfies the no K5, no K3 subdivision. Okay, so K5 only graph, only 3 connected G is K4, which is planar. Okay. Not too interesting base case there. We didn't even need to use the fact that it was free from those things there. Okay, so let's let n be greater than 4 and assume the statement of the theorem holds for graphs on fewer than n vertices that are 3 connected don't have this appropriate subdivisions. Okay, so now we use an important theorem that we proved when talking about 3 connected graphs. What do we know about 3 connected graphs and contractions? Contractions are obviously relevant here, right? They undo subdivisions. Moreover, contractions reduce the number of vertices, right? So I want to reduce the number of vertices and maintain a graph that is 3 connected and doesn't have those subdivisions, okay? So recall that 3 connected G, they always have an edge that you can contract and maintain the 3 connected property, right? At least if they have it more than 4 vertices, which they do in the case we're here, okay? Has an edge xy such that G contract xy remains 3 connected. Okay, this was the contraction lemma, I think we called it, in the chapter when we talked about 3 connectivity. Okay. Okay, so observe that G contract xy has fewer vertices than G, 1 less vertex. Okay, so in principle, we can apply induction. It's still 3 connected. It better be 3 connected or we can't apply induction, right? So this is one of the issues here. If your graph is not 3 connected, you don't have this edge to contract. There's no obvious way to go forward with the induction. I want to maintain 3 connectivity. So that's why we're doing the lemma here. And G still has no K5 or K33 subdivision. Okay. We already discussed this in some sense, but actually I'm going to leave thinking about this as an exercise, okay? And actually this is stated as an exercise in the notes there. It's not too hard to see, but you cannot create a K5 or K33 subdivision via contractions, okay? It's not totally obvious, but that is something that can be proved, okay? So this contraction won't create this forbidden structure. It won't create those subdivisions, okay? But that does require a proof, okay? But the point is, this G contract XY satisfies all the conditions of the hypothesis, okay? So by induction, G contract XY is planar. In other words, it has a planar embedding. So we can draw it without crossings, okay? Which is exactly what we want to do, right? So there is a planar embedding of G contract XY. Okay, so let's draw G contract XY and remove edges incident to the new vertex, say VXY, right? So when you contract XY, you get a new vertex VXY. Let's remove all the edges incident to that. Then let's think about our picture real quick. And I'm going to draw those edges back in a second. I just want to emphasize something. So Vxy is here sitting by itself, drawn somewhere, and it lives inside of a face. Whoa, right? It lives inside of a face. Or it could be on the unbounded face, like there's a face on which it lives. Now, what I claim that the face containing Vxy, after we remove these edges, is a cycle. That follows by 3 connectivity, okay? In fact, we know something even stronger. In fact, all neighbors of Vxy live on this cycle, okay? Then before I removed them, right? Let's think about this for a second. So this is via 3 connectivity. Maybe this part's a little bit hand-wavy, but the point is, say Vxy, the graph is connected, right? Because it's 3 connected. So Vxy like somehow has no choice but to reach out to this cycle here, right? It can't cross over, and it can't just like terminate inside of here. But if this was a path, after I remove this vertex here, what can you tell me about this path? Is the graph still 3 connected? Sorry, if I remove a vertex from a 3 connected graph, the resulting graph is, it's at least 2 connected, right? 2 connected graphs, all the faces have to be cycles in 2 connected graph. Because if any face has like pending stuff like this, like that is not something that's 2 connected, right? If I remove this vertex, this stuff gets disconnected from the graph. So all the faces have to be cycles. Moreover, if there were edges coming out of Vxy, and of course there are edges coming out of Vxy because the graph is 3 connected, those edges can't like be paths like this. They have to just go directly to the cycle. If they do anything other than that, then when I removed them here, or say removed Vxy, either way, I'd be left with this pending stuff here, which was not 2 connected. It was only 1 connected. So Vxy actually has no choice but to send its edges to this bounding cycle. Now, this cycle isn't a face in this graph. It's only a face after we remove those edges or remove that vertex, right? So, but the point is, there's a bounding cycle around Vxy, and Vxy's edges all go to that bounding cycle. And this relies completely on my graph being 3 connected. If my graph was 2 connected, or just connected, Vxy absolutely could send edges there. It might even just send edges and they stop. Like this is still planar, right? That's not like an issue, okay? But so we rely heavily on 3 connectivity to say that our picture looks like this. Okay. So, all right, we're going to use this fact here multiple times in the remainder of the proof. So let's scroll down a little bit here, and let me show you what the goal is here. Okay, so let's draw the cycle again. Here's C, and here's Vxy. And I know all the neighbors of Vxy are on the cycle here. Okay, in this planar embedding. So we're thinking about this is the planar embedding of G contract XY. And here's the cycle that we discussed there of the face that bounds Vxy when those edges are removed, and all their edges go there. So this implies that all the neighbors of X and of Y in G are on C. Now, I don't have a planar embedding of G. I'm trying to find that, right? I have a planar embedding of GXY by induction, by magic, but I want to find a planar embedding of XY. But X and Y's neighbors, they're definitely on this cycle, right? Because like what happens when you contract a vertex, the old edges remain. Actually, there could be duplicate edges, by the way. Of course, there could be duplicate edges. Although we usually remove those. Those don't have an effect on planarity, as we've already seen a couple of times. But the neighbors of X and Y are exactly the neighbors of Vxy, right? They're subsets of those things, right? Nothing changed. So what this actually means is we can do the following, and we're going to actually pretend that Vxy is, say, X. Okay? Now, all of X's neighbors appear on the cycle, and they're among these black edges. But some of these black edges may have been may be there because of Y, not because of X, right? So some of the black edges might be redundant. My goal here, though, is to somehow figure out, hey, can I draw Y here and it's joined to X, and then like something like this. That's my goal. I want to figure out how to draw Y that way. Okay, so I can pretend basically I've embedded the graph G minus the vertex Y, and all of X's and Y's former edges are there. I mean, that's what a contraction is. Okay, so that's the question I want to answer here is how do I, so okay, so pretend Vxy equals X. I mean, you can basically pretend this, right? When I contract a vertex or an edge, I can contract 2X or contract 2Y. And all that happens is X gets some new friends, right? It gets some new edges that weren't necessarily neighbors of it before, right? So this is like X with potentially some, like maybe if I draw, you know, say these green edges, these were definitely edges incident to X. But the black ones here were not, you know, not edges adjacent to X at first. They only got introduced because of Y when they got squeezed there, okay? But this still embeds the graph G minus Y, right? I mean, somehow, right? So the reason we didn't try to embed G minus Y though, why didn't we try to embed G minus Y? Because in a lot of ways, that's the obvious thing to do. Remove a vertex, embed the graph, and then replace, try and redraw Y in there. But why didn't we just remove Y instead? What's the reason for that? Because that's what we're trying to emulate here, basically removing Y. But why didn't I do that directly? The inductive hypothesis. Removing Y would not maintain 3 connectivity. So I wouldn't actually know that my graph was still connected. I mean, still planar, right, after I removed a vertex. It might be like fewer. Now, it's unlikely that if I can embed all 3 connected graphs, that somehow magically 2 connected graphs are bad, but like, it's possible. It's possible. Okay, so we don't have a ton of time, so let me go through this here. So the goal is to embed Y without introducing crossings. So I'd like to do that. Okay, so suppose I'm trying to embed Y, and it's like, look where Y is going to be. It's going to be in one of these pi pieces, but look at the obvious problems. What if Y, I put Y here and make it adjacent to X, and it's like, oh, Y's neighbors, you know, are this guy, and what about like this guy here? Like, how can I can't get there without crossing over, right? So okay, so all right, let's be smarter. Let's put it here. I can go there, but I can't get there, right? So like it seems like it's impossible. But what I'm going to show you is that if you have these scenarios where you're forced to get a crossing, you're going to get a K5 or K33 subdivision. And somehow you're going to have this nice scenario that Y just embeds very nicely into one pi slice here. That's the only situation. Okay, so let's do that real quick. To make things easier, let's name the neighbors of X, X1, X2. Okay, for now, these are all the neighbors of X, X3, X4, all the way up to ... xk. And then the paths between these things along the cycle, I'm going to give them names as well. So this is P1, P2, P3, and then up to the last one's PK. This is P4. Does that make sense? The paths along the cycle, this partitions it into paths. I mean, the paths share n vertices, but it splits up the crust of the pizza, right? Are these paths? Okay, and name them like that. Okay, so I want to address some cases here. So case 1, these cases are in different order than in the notes. Doesn't matter too much. So X and Y share 3 neighbors, A, B, C, on the cycle. Okay, so for each of these proofs, I'm just going to draw up the picture again. So here's X. It's got 3 neighbors, A, B, C. It has more neighbors, but it definitely has A, B, C. And let's say there's Y. And I don't know how, I'm not claiming that what I'm drawing here is planar, because it can't be, but I know this part's planar so far. And here's Y, and it's also adjacent to A, B, and C. Okay. Y is also adjacent to X, right? So I'm thinking about G now. But this picture here is a subdivision of K5, right? Because I've got vertices, I've got 5 vertices, and each of them are either adjacent by an edge or along a path, right? A is adjacent to B along this subdivided path. B is adjacent to C along this subdivided path. C is adjacent to A along this subdivided path. X is adjacent to everything, and y is adjacent to everything. So that's a subdivision of a K5. That's a contradiction. That can't happen. G doesn't have a subdivision of a K5. So if X and Y share 3 neighbors on C, and all their neighbors are on C, but if they share 3 neighbors, then I have a K5, sorry. Okay, fine. But maybe that doesn't happen. So here's the second case. Y has a neighbor, Y prime, on the interior of some PI, and a neighbor Y prime not on PI at all. Let me draw this picture. Maybe this would have been the better case to start with. So this case, again, is a problematic one. Here's X, here's XI, and XI plus 1. So this arc here is PI, right? And then I say I want to draw Y somehow. Oh, I'm missing an edge here. Y has a neighbor Y prime that's on the interior of PI, and a neighbor Y2 primes, which is not on that path. Now, this is going to be problematic because then how would I ever embed Y into my graph? It's going to be impossible, because if I make it adjacent to Y2 primes, I mean, I'm going to put it inside of here because it has to be adjacent to X. If I put it here, it can't get to Y2 primes. If I put it over here, it can't get to 1 Y prime, right? Remember the original picture I showed? Like this scenario will not be planar. I'm not going to be able to solve this one, at least with the picture that I have. So hopefully we can rule this out through other means, and it turns out we can, because then here's Y, and it's adjacent to Y prime and adjacent to Y2 primes and adjacent to X. And I claim that this is a K3 minor, because if I draw it like this, let me mix these up correctly. Let's put Y over here, X over here, Y prime here, Y double prime here, XI here, and XI plus 1 here. So 6 vertices. Y prime is on the interior of PI, so it's not equal to XI or XI plus 1, right? That's crucial that it was on the interior. If it was just on PI, then it might have been equal to those two things. I want to have 6 distinct vertices. And then if you check here, between any 2 vertices, you either have an edge or you have a path that's disjoint otherwise, and that's clear, right? So X is adjacent to everything on the opposite side. Y is adjacent to everything on this side. And then XI is adjacent to Y prime and Y2 prime by traveling around the cycle. Adjacent, I mean, there's a path, right? So Y, wait, what am I saying? Oh, yeah, Y is adjacent to those. Sorry, X is, no, I got that. What am I trying to say here? XI, yeah, okay. XI can get to Y prime and to Y2 primes, and XI plus 1 can get to Y2 primes and Y prime. So XI is adjacent by a path to there, and XI is adjacent to a path to there and there. And those 4 paths are pairwise disjoint because they go around the cycle. Okay, so that's a K3 minor, which is also a contradiction. Okay, now maybe I didn't address it, but this picture here was also problematic. If I went to 3 corners like this, then I wasn't going to be able to embed Y either. We have 1 remaining case, and then that actually ends the theorem, the proof. So case 3 says the following, that all the neighbors, this is the otherwise, right? If I don't have case 1 or case 2, this one has to be the only thing that happens. So let's say otherwise. This means that all neighbors of Y are on a single pizza slice PI. Okay? Let's just convince ourselves real quick that that's true. If you have one on the interior of PI and one not on the interior of PI, then you're in case 2. So all of them appear on PI, or the possibility is the first case. Because this interior condition was demanded here, I can avoid this interior condition if all the neighbors were at corners, right? Then nothing's on the interior, but then I have 3 neighbors here on 3 different corners. Okay? So now they all live on a single PI, And that could mean you only have two neighbors and they're both at the endpoints of pi, but that's fine. They're still both on pi. Okay. But in this case, we can do the embedding, because now here's x, here's xi, here's xi plus 1, and here's the rest of my cycle c. And all the neighbors of y are here, on here. They might correspond to xi and xi plus 1, but how do I finish my embedding? Well, now it's obvious. Put y here, join it there, and put it like this. And it's planar. Okay, so G planar. There's nothing inside of these regions, right? By 3 connectivity, we already established that earlier, that if I remove the edges incident to x, then my cycle out here is a cycle. So there's nothing, I mean, my face is a cycle. So there's nothing else here. So I'm lucky enough that I can actually squeeze it all into one portion here. In the other cases, when I couldn't squeeze it into one portion here, I either got a K33 minor or a K5 minor, which were the two things. I keep saying minor, subdivision. Every time I said minor, I meant subdivision. Yeah, I got these K33 or K5 subdivisions. So those were contradictions. And so I reduced myself to this very nice case, and I was able to finish the embedding. I think I maybe misstated one thing here when defining the drawing. So here, in this picture here, when I transformed Vxy to x, I should have just dropped all the black edges, those that were adjacent to y. They don't need to be there. I'm going to try to embed them after the fact. So these xi's were only the original neighbors of x on the cycle there. Okay, I hope that was evident. I mean, even if I pretend there are other things, it doesn't actually change the ladder. It's just unnecessary. So, okay, sorry about that. Held you guys, but that's the end of the proof.